A modern factory floor is a symphony of kinetic energy, but its most expensive sound is absolute silence. When an assembly line stops unexpectedly, the financial hemorrhage is instantaneous. Unplanned downtime costs global manufacturing an estimated $50 billion annually. It is a massive, invisible tax on industrial production, driven by the sudden, catastrophic failure of critical machinery. For decades, plant managers treated mechanical failure as an unpredictable force of nature rather than a solvable mathematical equation. The traditional defense against this chaos relies on two fundamentally flawed strategies. Reactive maintenance is essentially waiting for a machine to break and then scrambling to fix it while production grinds to a halt. Preventative maintenance is a calendar-based approach where parts are swapped out at regular intervals regardless of their actual condition. Both methods are incredibly inefficient. Reactive maintenance guarantees lost revenue, while preventative maintenance forces manufacturers to throw away perfectly good components, wasting millions in unnecessary labor. The underlying flaw in both traditional approaches is a profound lack of visibility. A massive industrial turbine or a high-speed robotic arm does not simply break without warning. It whispers its deterioration long before it fails. It vibrates at a slightly different frequency, its internal temperature spikes by a fraction of a degree, or its bearings emit a microscopic acoustic anomaly. The problem has never been a lack of warning signs. The bottleneck is the human inability to process the sheer volume of high-frequency data generated by industrial equipment in real time. This is where the architecture of the factory floor undergoes a radical transformation. The integration of the industrial IoT has wired these massive physical assets with thousands of microscopic sensors. Every motor, compressor, and conveyor belt is now a continuous data stream, broadcasting its operational health. But deploying sensors is only half the solution. A single manufacturing plant can generate terabytes of raw information, making continuous sensor data analysis a necessity, but it creates a digital noise floor so dense that no human engineer could possibly monitor it for subtle deviations. The raw data is entirely useless without a cognitive engine capable of interpreting it at scale. Manufacturers built a nervous system for their factories but lack the brain to process the pain signals. The solution is the deployment of predictive maintenance models powered by artificial intelligence. Machine learning algorithms are designed to excel exactly where human cognition fails, finding microscopic patterns inside oceans of unstructured data. By feeding historical sensor data into deep neural networks, AI learns the precise acoustic and vibratory baseline of a perfectly healthy machine. It maps the complex, multidimensional relationships between temperature, pressure, and kinetic output, establishing a baseline of normal operations within its latent space. Once this baseline is established, the AI monitors the live data feed with ruthless precision. It is not looking for a broken machine. It is hunting for the mathematical precursors to mechanical failure. A bearing that is weeks away from shattering will begin to vibrate at an anomalous frequency. To a human operator, the machine sounds perfectly fine. To the algorithm, the deviation is a blaring siren. The AI cross-references this microscopic vibration with historical models, instantly recognizing the digital fingerprint of an impending breakdown. This capability represents a monumental shift from reactive to proactive operations. The system does not merely alert an operator that a machine is acting strangely. It provides a highly specific diagnostic forecast. The algorithm can predict that a specific spindle on a milling machine will fail in approximately 72 hours if the current load is maintained. This transforms an unexpected catastrophe into a scheduled, highly controlled maintenance event. The operational advantages of this foresight are staggering. By predicting breakdowns days in advance, manufacturers can optimize maintenance scheduling to align with planned production lulls. Replacement parts can be ordered and staged before the machine is ever taken offline. Maintenance crews are deployed with surgical precision, knowing exactly which component is degrading and exactly what tools are required to fix it. The chaotic scramble of emergency repairs is replaced by the calm execution of a targeted intervention. Equipment lifespan is dramatically extended. When anomalous friction is detected early, a simple lubrication routine can save a $100,000 motor from tearing itself apart. Manufacturers no longer have to guess when a part might fail, entirely eliminating the waste of calendar-based preventative maintenance. They extract the maximum possible utility from every single component, replacing parts only when the algorithm confirms they are genuinely at the end of their life cycle. This intelligence revolution triggers a profound evolution in the daily workflow of the factory floor. The role of the maintenance engineer is being fundamentally rewritten. Historically, these professionals were highly skilled mechanics reacting to physical symptoms and diagnosing problems through manual inspection. Today, their primary interface is increasingly a digital dashboard. They are transitioning from wrench turners to data-informed asset managers, using AI as an omnipresent diagnostic partner. The physical labor remains essential, but its deployment is now hyper-optimized. An engineer no longer walks the factory floor listening for strange noises or manually checking temperature gauges. Their shift begins by reviewing algorithmic triages. The AI dictates the priority list, highlighting the most critical vulnerabilities across the entire facility. This allows a small team of technicians to effectively maintain a complex industrial footprint that would have previously required an army of inspectors. The velocity of production is fundamentally altered by this predictive capability. In a traditional setup, a single failed bearing could halt an entire automotive assembly line, idling hundreds of workers and bottlenecking downstream supply chains. Every minute of that unplanned downtime bleeds capital. When AI predicts that same failure in advance, the repair is scheduled for the third shift during a planned changeover. The assembly line never stops. The cascading benefits extend far beyond the walls of a single factory. Supply chains are tightly coupled ecosystems, where a delay in one facility creates a ripple effect of shortages globally. By ensuring continuous production, predictive maintenance stabilizes the entire industrial network. A manufacturer that can guarantee its output schedule secures a massive competitive advantage over rivals still struggling with unpredictable mechanical failures. The financial impact is undeniable. Facilities implementing these systems routinely report reductions in unplanned downtime by up to 50%, alongside double-digit decreases in operational expenses. It is a technological integration that pays for itself almost instantly. Yet integrating this level of algorithmic control is not without friction. The primary challenge in the early stages of deployment is algorithmic oversensitivity. A factory is an inherently noisy environment. If an AI model is not trained with enough contextual data, it will flag every minor fluctuation as an impending disaster. This barrage of false positives can quickly erode trust on the factory floor. If engineers are constantly dispatched to fix healthy machines, they will simply start ignoring the system. To combat this, modern predictive systems utilize advanced techniques like zero-shot inference and continuous reinforcement learning. The models are constantly updated, learning from the specific environmental quirks of the facility they monitor. When an algorithm flags an anomaly and an engineer confirms it was a false alarm, that feedback is integrated into the neural network. The AI learns the difference between a failing motor and a motor that simply runs a little hot during the summer months. This creates a critical period of calibration where the human and the machine must learn to collaborate. The greatest systemic risk is not that the AI will fail to detect critical faults, but that human operators will allow their own biases to override the algorithm's warnings. A veteran mechanic might look at a machine, rely on 30 years of intuition, and decide the AI is wrong. When that machine subsequently shatters, the cultural cost is as high as the financial one. Overcoming this cultural resistance requires a fundamental shift in industrial leadership. Management must champion the transition, proving to the workforce that AI is not a tool designed to replace their expertise, but an augmentation designed to elevate it. The algorithm provides the microscopic visibility, but the human provides the physical execution and contextual judgment. The most successful manufacturing facilities are those that seamlessly fuse algorithmic precision with human mechanical mastery. As this trust solidifies, the factory floor becomes a highly synchronized environment. The adversarial relationship between man and machine is replaced by a cooperative dynamic. The machinery actively communicates its needs. The workforce responds not with frantic emergency measures, but with calculated, preventative care. It fundamentally changes the psychological reality of industrial work, replacing constant anxiety with predictable control. The culmination of this technology is the realization of a truly intelligent manufacturing ecosystem. We are moving away from static assembly lines and toward dynamic, self-diagnosing physical networks. When a factory can accurately predict its own mechanical failures, it ceases to be a collection of isolated tools. It becomes a unified, living organism, capable of protecting its own operational integrity and maximizing its own efficiency. The factories that master this predictive capability will dominate the future of global production. They will operate faster, cheaper, and with a level of reliability that legacy competitors simply cannot match. Unplanned downtime will soon be viewed not as an unfortunate accident, but as a failure of intelligence. In the modern industrial landscape, the most critical tool is no longer the wrench, but the algorithm that tells you exactly when to use it.